Hello and welcome. Just to introduce myself, my name is Rhiannon Carlisle. I'm with Conservation Nebraska's Common Ground program. Just a little background about Conservation Nebraska. We are a nonprofit organization, and our focus is on educating the public, supporting communities, and increasing civic engagement. All of this to help protect Nebraska's natural legacy. Some technical things about the webinar. You are muted and have your cameras off, so we cannot see or hear you. If you have any questions throughout the presentation, you can go ahead and put them in either the Q&A or in the chat box. I will be monitoring these throughout, and we will answer them at the end of the presentation. And lastly, we are recording this webinar. We do post these videos to the Conservation Nebraska website and to the YouTube page, so anyone who couldn't attend can watch it there, or if any of you guys would like to, you can go ahead and re-watch it. And lastly, at the end, there will be a quick 1-minute 3-question survey that we really appreciate if you guys could take. It helps us gauge our outreach and helps give us some feedback about these webinars. All right, so joining us today is Aaron Young with the University of Nebraska-Lincoln. I'm going to go ahead and let Aaron introduce himself. So you can go ahead and start whenever.
All right, thanks. Good afternoon. My name is Aaron Young. I'm a geologist with the Conservation and Survey Division at the University of Nebraska-Lincoln. In other words, that's a fancy way of saying Nebraska's Geological Survey. I've been doing this now for going on 14 years. For the last 11 of those 14 years, I've been running the groundwater level monitoring program for the state of Nebraska. And it looks like, I can't share my screen.
All right, let me see. There you go. You should be able to share now.
All right, there we go. Okay, so today we're going to talk about groundwater in Nebraska. I'm going to mainly focus on the High Plains Aquifer. We'll talk a little bit about some of the other aquifers in the state. We're going to talk a little bit about background. So what is an aquifer? We're going to talk about how the High Plains Aquifer formed. So if you understand some of the geology behind how the aquifer formed, it's a lot easier to understand some of the resource and how that's used and managed and accumulated. We'll talk about how much groundwater Nebraska has and the status of groundwater levels in the state's aquifers. And one of the big questions that I always get is if there's, say, a chemical or an oil spill in, a North Texas oil field, is that going to pollute the aquifers in Nebraska? So we'll talk a little bit about that, and that involves how water and pollution moves in the aquifer. And last, we'll go over some online resources where you can go look at some of this information. So I always like to start these talks off with this slide, and I know this seems like it might be a little bit obvious, but there was a time that I was actually asked this question by a national science advisor for a national publication. I won't mention any names, but this always comes up in the print that groundwater is supposed to be this giant underground lake, and it puts this image in people's heads that we're floating on this giant underground lake, and that definitely isn't the case. I'm not saying that there aren't places on Earth where we have like in the picture, underground caves that are filled with water, but we're not floating. That here in Nebraska, that's definitely not the case. In reality, so this is taken right out of my hydrology textbook, an aquifer is a body of rock or sediment that contains sufficient saturated permeable material to conduct groundwater and yield usable quantities of water, wells, and springs. So what that actually means, to simplify things a little bit, is let's see here, this is kind of a breakdown of what our aquifers look like. So for most of Nebraska, most of the High Plains Aquifer, that's going to be a sandstone aquifer. So in that sandstone, we're going to have grains of sand, which would be the gray particles here. And between those particles, we have pore spaces. Those pore spaces are connected. So that would be the permeable part of this definition. And those spaces, since they're connected, water can flow through them. It is flowing with some resistance, but it can flow through them. So this is a pretty typical picture of sandstone that makes up the High Plains Aquifer. And you might be a little bit confused. So a lot of people refer to as the Ogallala Aquifer. The true technical name from the USGS is the High Plains Aquifer. The aquifer itself is made up of many different geologic units, of which the Ogallala Formation is a big part of, but it really is many different formations that are all hydraulically connected, but are all combined into one. So this picture is actually the Ogallala Formation, and this is kind of a representation of what this sandstone looks like if you were to blow it up probably 100 times or so. And I'll talk a little bit more about this picture as we go on. So once again, Nebraska's aquifers as a whole are comprised primarily of three materials. By far and away, the largest one of those is sandstone. So these are things like the Ogallala group sandstone. In eastern Nebraska, we would have things like the Dakota group sandstone, or out in far western Nebraska, the Arikari group. There's some others in there as well, but those are the common ones. We also have unconsolidated sands and gravels, or quaternary sediments sometimes are called. Basically, that means geologically young sediments. In our case, essentially over the last 2 million years or so. And these would be things like glacial sediments, coarse river deposits, sand and gravel. And in eastern Nebraska, below some of those glacial sediments, we have some paleo valley deposits. I'll explain a little bit more about what those are here in a few slides. And to a much lesser extent, in certain parts of Nebraska, we have fractured limestone aquifers. So instead of having sandstone aquifers where the water is stored between individual particles, like in these images, that water is stored in fractures. So limestone is massive, so it doesn't have particles. What happens is that limestone fractures over time, and when you put your well into it, your well is going to go through and it's going to intersect some of those fractures. And water moving through those fractures is what supplies water to your well. Generally, limestone aquifers like this don't yield very large quantities of water, but if that's the only source of water that's under your feet, generally it's enough to get by with a domestic well. So how do we know all this? How do we know what's under our feet? So the Conservation Survey Division, or CSD, has had test hole drilling program that's been ongoing since about 1930. So over the past 90 or so years, we've drilled and logged about 5,600 test holes all over Nebraska. So these test holes start at the surface and they go down to bedrock and usually continue on 20 or 30 feet in the bedrock. We have our own drill rig. Generally, somebody like me or one of my colleagues will sit at the bottom of that drill rig with a little soup strainer and catch all the sediment as it's coming up. We then take that sediment, we lay it out and we describe it. So the picture on the right here, that's sand and gravel. As that material comes up, a lot of times it gets sorted. So the lighter material over here, these finer sands will come up first and then followed by the coarser material. This is a fairly common sand and gravel unit for the High Plains Aquifer in eastern Nebraska. So this is just a little bit west of Crete. This would be some of those younger sand and gravel deposits. These are Platte River in origin, so they're deposited by the Platte River. And this is a pretty good illustration of what our aquifer material actually looks like. So you imagine, water being contained between all these little individual grades. So an aquifer, in addition to yielding water, in a way kind of acts like a giant battery. So in the water cycle, generally there aren't many places where water can stop and be held and stored in a place where it can be used. So this is a good thing. So in times of drought, we still have water under our feet that we can pump and use. You know, will last many years. And then in times when it's really wet, all this water that's coming down is precipitation. So precipitation is our dominant form of recharge for our aquifers. That precipitation can come in and fill in, you know, what we've used in the dry years. So it acts as a giant reservoir, much in the same way that, you know, we have surface water reservoirs. So here in Nebraska, primarily our aquifer that covers the vast majority of the state is the High Plains Aquifer, and that's shown here in blue. We do have some smaller aquifers. When you're over here in the eastern part of the state and you're in a place such as, you know, under our feet in Lincoln, we don't have the High Plains Aquifer, so we have to look elsewhere for groundwater. The brown here would be the Dakota Aquifer. So that's a fine sandstone unit. Generally, this is just going to supply domestic wells. There are a few irrigation wells that are in the Dakota Formation, and generally they work okay, but in dry years, they can have some trouble. Some of the other aquifers here would be the pink lines. These pink areas are what are called Paleo Valley aquifers. Most of these are fairly old, so pre-glacial in Nebraska, so, you know, two plus million years old. They're sand and gravel. They're generally very loose and very coarse sand and gravels. These tend to yield very large quantities of water, and pumping them doesn't seem to have a huge impact on water levels for the most part. There are some exceptions, but generally speaking, these will yield water for both domestic and irrigation wells, no problem. So when you're driving around in these areas, a lot of times you see pockets of center pivots, and generally those center pivots are over one of these paleo valleys. Lastly, for some of our secondary aquifers, we have a handful of wells in Nebraska that are in this orange unit up there and down near the Nebraska-Kansas border. And these are one of our limestone units. So this is the Niobrara chalk, or Niobrara limestone, as it's usually called. And these, once again, would be those fractured limestone wells. And we really don't have many wells in it, but if you're in an area that doesn't have any other source of water, these become very important. So once again, to understand how the High Plains Aquifer works and how it stores water, it helps to understand a little bit about how it formed. And I really like this picture of the Platte River. So most of the sediment that makes up the High Plains Aquifer came from the Platte River. And if you look at this picture, we see all these sandbars. You know, this is all sand that has been deposited as the river is flowing. So kind of keep that in mind as we go through some more of these slides. So we're going to start off here with some very basic sedimentology. And, you know, keep in mind here that, you know, what I'm going to go through in the next 3 or 4 slides is something that as a grad student, we would go through in 3 or 4 semesters. And indeed, you know, you could certainly write a dissertation on any one of these portions. So, you know, some of these things have been pretty grossly simplified, but it'll give you the general idea. So in order for deposition to take place, we have to have a couple of things. First of all, we have to have a source of sediment. And in our case, that's going to be the Rocky Mountains. So about 65 million years ago, some tectonic forces in the central part of the continent came together, and it started to push the land up. The minute you have land that is higher than its surroundings, Mother Nature is going to start working on that bump, and it's going to start breaking it down and eroding it away. So as that land is being pushed up, the forces of nature are constantly working on it. So we have processes, think, freezing and thawing of water makes rock break apart. We have water erosion that's over time, that's removing a lot of sediment. We have chemical breakdown, so some minerals in rocks break down easier than others, and that's pulling that material away. As that material breaks down, it's starting off up on the top of this hill or mountain, and at that point, that sediment has a lot of potential energy. So particles are going to want to be transported from areas of high potential energy to areas of low potential energy. So it's basically a fancy way of saying water flows downhill. When it moves from this area of high potential energy and it gets down to the bottom, we're going to have our area of low potential energy. When you get to that area of low potential energy, the water in this case that's carrying that sediment can't keep that sediment in suspension anymore. It drops out of suspension and it gets deposited. So the other thing that you need to have sediment accumulate is somewhere to put it. So in sedimentology terms, this is called accommodation space. So in this case, we have our area of low potential energy is going to be this corner here right up against the side of our mountain. So we have some other sources of sediment as well. In western Nebraska, we have lots of layers of volcanic ash in the geologic record. Those certainly accumulate here. Some biogenic factors, so breakdown of calcium carbonate, for example, in soils can accumulate, both as a primary sediment, so that's something that can be deposited by water, or as a secondary sediment, so it would be something that would form, say, in sandstone to cement the grains together. We also need a transport mechanism. So the vast majority of this sediment, in our case, is going to be transported by water. Wind is also a factor, so we do see sand dunes and essentially loess that has been turned into rock in the rock record. So we see the formation of the Nebraska sandhills. That's actually a modification of sediment, but that counts as a transport mechanism as well. So keep that in mind here as we go through the next couple slides. So this is kind of a illustration. This is a real world illustration of what I had in that last slide. So up here in the top, we have a mountain range. So this is in the desert southwest down near the Mexico border. We have some water down here, and then we have a flat plain. In the middle, we have this area here, and this is our corner between the mountain range and the flat area. And what we see accumulating here is sediment that's being washed out of the mountains. So we get these fan-like features. These are referred to as alluvial fans. The big one here in the middle. There's a bunch of them that are kind of coalescing along the sides. So we have our area of high potential energy. That sediment is being transported down by water. It loses that energy and is deposited in this giant alluvial fan. And that's building up away from the mountain and into our plain. So if we go back 65 million years or so, we see the Rocky Mountains start to form. And as they are lifted up, the Rocky Mountains start to erode. All that eroded material gets washed downhill and gets deposited in what is essentially one very giant alluvial fan right along the flank of the Rockies. And this is kind of a generalized cross-section across the state of Nebraska. And we can see that alluvial fan is right here. So basically this gray material, this giant wedge. So if we look at that a little bit closer up here, this topographic cross-section across the state, across this white line, is represented down here in the bottom. So Nebraska is roughly in the middle here. And once again, we have the Rocky Mountains over here to the west. Those are, call it about 7,500 feet or so. Over in the east, we have essentially the Platte River, and that's somewhere around 1,000 feet. So once again, we have our area of high potential energy. That material is being washed from west to east by the Platte River, and it's being deposited as fill in this corner between the uplifted Rockies and the flat plains. If we look on this aerial imagery here, if you squint your eyes just right, you can kind of pick out there's this big alluvial fan feature that's coming off of the Rocky Mountains, kind of goes through this way. So we can even see this today as the Platte River moves across the land surface, it's depositing this material. We can see this in the geologic record that the Platte River has kind of swept across the land surface from south to north and back and deposited this material, as well as some of the other river systems that come out of the Rockies into the plains. In the rock record, we can actually pick this out. So if you remember back to all those sandbars in the Platte River I was showing you, if you look at this layer right here, we can see these lines at almost a 45-degree angle here. What those lines are is the lee side of that sandbar. So what this is telling me is there's a layer right here. Here's the top. I know it's a little hard to see in this picture. Here's the bottom. That one's a little bit more clear. That layer was a depositional unit of the Platte River, or the ancestral Platte River, when it was at this location. Same things up here. We can see more cross bedding from those sandbars. And here's yet another layer. So it's just layer after layer of the Rocky Mountains moving up, the Platte River moving across the surface and depositing layer after layer of sand and gravel. Over time, that sand and gravel becomes cemented and we end up with sandstone. You can see this in the geologic record. So once again, we see it in the picture here, and we can actually see this in our drill cuttings and cores that we take from the subsurface. This is the Nebraska sandhills, and we can pick out these units in Nebraska sandhills. We can also pick these paleo valleys or paleo channels out in the rest of the state. And once again, we can kind of see the Platte River working its way from north to south through time and depositing that material. So the Platte River system deposited much of this material. As we move south, other river systems, work their way depositing that material from west to east. And this is the High Plains Aquifer as a whole. So that's kind of a quick overview of how the aquifer formed. As I talk through the rest of this, keep that in the back of your head. So understanding how the aquifer formed can really give you a better idea of how this resource works and how it's managed and how we can best use it and conserve it. So the next question that comes up is, how much groundwater does Nebraska have? The short answer to that is Nebraska has a lot of groundwater. However, although we have a lot of groundwater, it's vast, but it's not infinite. So to put some numbers on that, the High Plains Aquifer as a total has about 175,000 square miles. It covers about 175,000 square miles under parts of 8 states. By area, Nebraska has right around 65,000 square miles, or something like 36% of the total area. In that 36% by area of the High Plains Aquifer, we have right around 2.4 billion acre feet of water. So 1 acre foot of water is the amount of water it would take to cover 1 acre of land with 1 foot of water. That's 69% of the total volume of the entire High Plains Aquifer. So if you want that, put that in a little bit of perspective, I know that's kind of a hard number to wrap your head around. In gallons, that's this gigantic number right here. The Platte River, where it flows into Missouri at Plattsmouth, on average flows at about 8,000 cubic feet per second. At that average rate, that's right around 326 years of flow of the Platte River. So for me, I grew up on the shores of Lake Michigan. I think of big bodies of water. I think of the Great Lakes. To put that in perspective a little bit differently, that's the volume of Lake Ontario and Lake Erie combined. So for those of us from Nebraska, that's these two. That's almost as much as the volume of Lake Michigan. Lake Michigan's quite a bit deeper than the other two, so it doesn't quite reach that level. But once again, Nebraska has a lot of water. So look at this a little bit differently. Cherry County in Nebraska, the one outlined here in red, sits over part of the very thickest part of the High Plains Aquifer, not just in Nebraska, but the aquifer as a total. This area here between Grant, Hooker, and Cherry County is the thickest part at a saturated thickness of right around 1,000 feet. Just in Cherry County has 287 million acre feet of water. So that's just that county alone. If we look at that in comparison, that's 17 million acre feet of water more than what is available in the High Plains Aquifer in Kansas. Now, Kansas does have other aquifers, much like Nebraska, they have other sources of water, but this is still a pretty significant chunk of it. That's almost as much water as what is available in the High Plains Aquifer in Texas. And to put that in perspective, that's roughly 75% of the volume of Lake Erie. So that tells us how much water we have. Now let's look at how our water resources change through time. So to do this, the state realized very early on that Nebraska's groundwater resources are very valuable. It's something that we need to conserve. So the Nebraska Groundwater Level Monitoring Program began back in 1930. Currently, it involves 30 different state and federal agencies. Those include us at CFD. I personally go out and measure around 100 wells in eastern Nebraska every year. All 23 of our natural resources districts, U.S. Bureau of Reclamation, 2 of Nebraska's public power and irrigation districts, and the USGS. So we collect annual groundwater level readings in about 5,500 wells, depending on the year, and then we compare those with previous years. So since 1900, CFD has amassed about 780,000+ hand measurements from more than 24,000 wells statewide. So once again, Nebraska's groundwater resources were something that was seen as valuable very early on. So this image comes from a Nebraska State Planning Board report. This is from 1941. The opening statement in the water resources section is groundwater is one of the most important resources of Nebraska. Some authorities suggest that it is of greater importance than the soil. And just to realize just how profound that statement is, this is before we were using groundwater for irrigation in Nebraska. At this time, there were only a handful of groundwater irrigation wells in the state. So having that vision that Nebraska would be depending on groundwater for agriculture and for its economy into the future is really something that is unmatched in the country. This map is showing groundwater observation wells for the groundwater level monitoring program back to 1938. I don't know how many dots are on this map, but for a state this size, that was a very robust program back in the 1930s. And that was something that, once again, was really unmatched anywhere else in the country. Believe it or not, I actually still measure a lot of these same dots today, which for this sort of data having close to 100 years of continuous, in many cases, continuous recorder data is extremely valuable information. So why go through all this effort? This is a really time-consuming and expensive program to monitor groundwater levels. However, Nebraska currently, or as of 2012, this is unfortunately the most recent data we have. The Census of Agriculture should be putting out their more recent numbers here, hopefully this fall. Nebraska leads the nation in irrigated acres. So we have 8.3 million irrigated acres. We're beating out California by a fairly large margin. To those 8.3 million acres, we're applying 8.1 million acre feet of water. That's 7.4 million acre feet from groundwater, and that's drawn from more than 96,000 irrigation wells statewide. The other 700,000 or so acre feet of water is coming from surface water sources, that being primarily the Platte River system and a little bit from some of the other rivers, the Republican and some of the smaller tributaries. So overall, the prosperity of Nebraska's economy and Nebraska's 15,000 plus farms depends heavily on groundwater for irrigation. So once again, as of last week, there's 96,452 dots on this map, and those are all our active irrigation wells statewide. So if we look at this as far as a density perspective, this area here in the Platte River where we see oranges and reds, unfortunately my legend didn't show up on this map, I apologize for that. This area of red here is greater than 16 irrigation wells per square mile. That's one of the densest areas of irrigation wells in not only Nebraska, but also North America. You know, so some of these areas in yellow are 4 to 8 irrigation wells per square mile. This is some of Nebraska's most productive farmland here in the southeast corner of Nebraska and south central Nebraska. So we're relying pretty heavily on our aquifer for groundwater here. So managing this groundwater, using this information wisely is really important. Today, you remember what that map looked like back from 1938. This is our current groundwater monitoring network. As of spring of 2021, which at this point is our most recent data, we're currently in the process of collecting data for spring of 2022. Last spring, we had 4,968 wells that were measured consecutively at least 2 years. So we may not have the most wells measured of any state in Nebraska, but density-wise, for observation wells, we're definitely near the top. So we take all this information every year and we put together a report of how groundwater levels change in Nebraska. We do that at several time scales. And this is the smallest time scale, and frankly, this is my least favorite map. So once again, you know, science is mostly statistics, and you can make statistics show whatever you want. This map, unfortunately, is showing a very, very small time snapshot of what's happening in our aquifers. And it looks like there's a lot of red on this map. So once again, aquifers are acting kind of as a giant battery. So during times when we have lots of rain, water levels come up a little bit. During times when we have not so much rain, groundwater levels go down a little bit. So last year certainly was not exactly a wet year. We had below average precip, and our groundwater levels went down a little bit. And you know, from looking at this map, you could look at that and say, oh, you know, we're in big trouble, you know, we're going to have problems, and that definitely is not the case. What we're actually looking at here is a decline from almost record high water levels due to the flooding that we experienced in 2019 and 2020. And we're seeing water levels that are actually coming back to a sort of long-term average. So despite the dryness last year and the declines that we see, if we go out a little bit and we look at a 5-year change map, we're seeing a lot of green on this map, and we're actually seeing, you know, water levels rising, you know, 5, 10, 15 feet almost statewide. We do see some declines over here in the eastern part of the state, and generally speaking, that has to do with declines associated with that flood water leaving the Missouri River floodplain and causing that decline to show up. We do have some problem areas in Nebraska. So Box Butte County in the southwest part of the state do on average see declines yearly of about 1 foot. And that's been linear for about the last 75 or 80 years or so. We take one step further back in time. Now we're looking at a 10-year change map. We're looking at this 10-year change map, and actually we're seeing a lot of green yet. This is despite having the year of 2012 and 2013, which were the hottest and driest year on record for Nebraska. So despite this extremely dry year, We had several slightly above average years in there, plus 2019, which was way above average. That includes the declines that we saw in spring of 2012 to 2013. Once again, that the decline or the rises that we saw from those floodwaters in 2018 and 2019. This was the map that followed those unprecedented flooding events. What we're looking at here actually missed a lot of the flooding. So in reality, this map actually should be a lot greener than what it is. But when we put all this information together, we see groundwater levels in Nebraska really don't change all that much. At least in my opinion, the best map out of this series is this one. And what this is showing is groundwater level changes from today, or in this case, spring of 2021, back to a time before groundwater was used for irrigation in Nebraska. And this is where the visionaries of that 1938 report really come into use. We have a baseline for what groundwater looked like in Nebraska a long time ago, and we can compare that to what it looks like today. And generally what we're seeing is groundwater levels in the sandhills are actually slowly rising. We see groundwater level rises around major reservoirs, so around the Calamus here in central Nebraska. We see some pretty significant rises around unlined canals and reservoirs in south central Nebraska. We've actually seen rises of over 120 feet. We see significant rises around Merritt Reservoir and Lake McConaughey. On the flip side, we also see some declines. So once again, we have some problem areas in Box Butte County and southwest part of the state. This should be red. I'm not really sure what happened there. Some of my screenshots, it looks like today, are having some issues. These areas up here, the greatest area of decline in Nebraska is just north of Alliance, and that's right around 126 feet. Similar in this area, we have declines of around 100 feet. Those are areas that are pumped for irrigation. That pumping is leading to a decline, once again, fairly linearly of about 1 foot per year. We also see some declines in that area of the state with the high density of irrigation wells. This area has been interesting. So most of the declines in this area took place up to about 1980. Since 1980, some of these areas have actually been coming back up, particularly in this area where we see water levels are actually higher now than they were back 80, 90 years ago. And the rest of this area has been either rising or staying generally at a long-term average, not going down. And there's several reasons for that. So over the past 40 years or so, we've had quite a few wetter than average years. That definitely helps. In that time period, we've also seen a movement away from flood irrigation and a movement towards center pivot irrigation. So we're using our groundwater much more efficiently. And all these factors kind of combined, we've also, I should say in that time, have developed the Nebraska Natural Resource Districts, and we've put in place restrictions on how much water we can pump. So all these factors combined have led to this area, once again, either staying the same or generally kind of rising a little bit. Some of the other areas, particularly in the Platte River Valley, are a little bit more variable. So some years we see some declines there, some years we see some rises there. That's a general state of groundwater in Nebraska compared to some of the other states, particularly our states in the south, Kansas and Texas, Oklahoma, we're in much better shape. Some of those other states have seen several hundred feet of decline, and in some areas they have seen aquifers that have become depleted to the point that that aquifer is no longer usable. Here in Nebraska, once again, we do have some problem areas, but we've not seen anything of that scale yet. We really haven't pumped out aquifers to the point that they're not usable. So this last question, so once again, one of the big questions that I get is, can a contaminant spill somewhere else in the aquifer contaminate the drinking water that we have in Nebraska? And the answer to that question is no. And keep in mind what we've talked about in the earlier part of this presentation. And I'm going to go through how water and contaminants can move through the High Plains Aquifer, really through any aquifer. And hopefully you'll get an understanding of how that works. And from there, you'll see that that really doesn't happen. So in hydrology, generally we think of water movement through an aquifer over the surface as the movement of a particle of water. So that particle in reality doesn't really exist, but just imagine, a couple of atoms are moving along here in these various ways. So if we have a particle of water and we drop it up here on our cross section at the top of this hill, very much like that particle of sand we were talking about before, moving off of the Rocky Mountains, that particle is in an area of high potential energy. So it's going to want to release that potential energy. It has a couple options to do that. So the first option is it can move as overland flow. So it's going to travel from high potential energy to low potential energy. In other words, water travels downhill. It's going to flow perpendicular to the topo lines here, or equal lines of elevation. And that water particle is going to move down from where it lands up here in the hills down into the river, where it's going to be carried away, and the water cycle is going to begin again on that particle of water. The other option is that particle can hit and it can infiltrate. So from there, it has a few options. It can travel down slope. It can travel to our river, be discharged into a river at base flow. That's going to be weeks to decades, maybe even a little longer, as opposed to hours to days as far as our overland flow. So that particle, if it infiltrates as shallow subsurface flow, instead of moving as perpendicular to our topo lines, is going to move perpendicular to our lines of equal elevation of the water table. So in this case, that would probably look something more stretched out like that. So this is at the very, very large scale. So this is less than a section. This is roughly 3/4 of a mile by 1/2 mile. So now if we take a step backwards, look at this from a little bit bigger perspective, this is all of these slides are coming from the Nebraska sandhills. It's just kind of what I had on hand, but this would work elsewhere in the aquifer as well. This is the Loup River Basin. We're looking at basically a couple of pixels before, right where the red dot here is at the end of this arrow. And what we're starting to see is, generally speaking, the water is moving from west to east. So remember, the slope, we have this giant alluvial fan coming off the Rocky Mountains, slopes west to east. We do, however, have some flow going from north to south or south to north, as we have in the middle between the rivers here. We have high areas. Those high areas are areas of high energy potential, and we're moving to areas of low potential energy. So although we do get these very localized north to south flows, the overall flow pattern for both at the surface and in the subsurface is going to be west to east. So now we're going to take a further step back here. So before the Loup River Basin, I'll go something about like this through this image. This is the Sandhills and western Nebraska. This red line here represents a cross section, and that cross section is right here. So this cross section cuts through the High Plains Aquifer. So basically all the units on this map that are not a shade of green make up the units that comprise the High Plains Aquifer. So we have some Aeolian sand at the top, or dune sand. We have the Ogallala group. We have the Brule Formation, some other minor groups. All these together make up the High Plains Aquifer. And once again, say our particle of water lands up here in the sand dunes, it can either make its way off as overland flow to one of the rivers, be transported back to the ocean and start the water cycle again, and make its way into the shallow subsurface, do the same thing, or it can make its way down deeply into the aquifer, where it's similar going to travel downhill from west to east, and it's eventually going to be discharged at the far end of the aquifer and start the water cycle over again. So whereas in shallow subsurface flow, we're looking at days to, centuries to maybe a couple of thousand years. Once it gets deep into the aquifer like this, we're looking at transport rates of, inches to feet per year. So that water might not see the light of day again for tens of thousands to millions of years at that point. So if we take a step further back and we go back to this image, now we have this rough cross section of the High Plains Aquifer. We know water moves downhill. Water is going to be transported from west to east. So even if that's not the case, so say we have, something that can make the water defy physics and move in a different direction. Some areas in the aquifer, so for instance, here in Kansas, also under the red line here that makes up the Kansas-Nebraska border, and some areas in Texas and Oklahoma, some of the modern day river channels have actually cut all the way through the aquifer and into the shale beneath. So those areas separate different regions of the aquifer, and water cannot pass those impermeable areas where there is no shale or is no aquifer. Furthermore, through parts of Kansas and Oklahoma, there's old faults in these areas. Some of those old faults cause some offsets. So these faults aren't moving today, but they have in the past. And those faults create structural offsets. So in order for the water to flow south to north to get past those, it would have to flow up and over the land surface and back down again. And that just simply doesn't happen. So once again, water moves in the High Plains Aquifer from west to east. And it looks like we're definitely getting down here on time, so I'll skip over this one. More information, I can bring up our data map here very briefly. So if you go to go.unl.edu/groundwater, it'll take you to our data map. That map will come up. You'll have to agree to the disclaimer. And from here, you can look at all of the information that I presented today. So these are our 5,600 or so test holes. You can click on them and get all the information for those. All these other layers, we have the water level change maps. We have all of our maps are in here. All the individual water levels that make up those maps, by clicking on the blue dots, you can see what the water levels look like at that location. And we have our geology and a bunch of other information. If any of you want to take a look at this, if you have questions, feel free to email me. And with that, I think I'd be happy to take any questions you may have.
All right, thank you, Aaron. I don't see any questions in the chat or in the Q&A. As I mentioned earlier, I'm going to send out a quick survey that lasts about 1 minute for you guys. If you guys could go ahead and answer that, that would be great. And if you guys have any questions, feel free to go ahead and ask them now. All right, not many questions. That's all right. I want to thank everyone for taking your time out of your day to come and watch and listen to this. If you guys want, you can go ahead and check out Conservation Nebraska's website or our YouTube page. As I said, we have a lot of our webinars posted up there. If you guys want any more information about any topic that you might be interested in, you can also go back and rewatch this. Later, we'll post it in a few weeks. We'll go ahead and finish up with this survey. All right, and I think that's good. Thank you, everyone.